Hello everyone. The topic for today is Maxwell relationships in thermodynamics. In this video, we will discuss the derivation of four Maxwell equations which are based upon internal energy, enthalpy, work function and free energy, and we will try to find out the mathematical procedure for using these differentials to obtain these four Maxwell equations. These four equations are well known in thermodynamics. Now let's have a look at the mathematical procedure for the derivation of these equations. Now, to prove this first Maxwell equation, we will start from du is equal to TdS minus P dV. Now, we will modify this equation to obtain Maxwell equation. Now, if in a process volume is constant, then that means change in volume is 0, then the above equation gives you du is equal to TdS or du by ds at constant volume, that is equal to temperature. Now, differentiate this equation with respect to V, which will give you curly square U upon curly S into curly V is equal to curly T by curly V, since now the entropy is not changing. So, mark this equation as number 1. So, once again, to obtain the second part of Maxwell equation, now if entropy change is 0, that is entropy is constant, then du becomes minus P dV or du by dV at constant entropy is equal to minus P. Now differentiate this equation with respect to entropy. We get curly square U divided by curly V into curly S, that is equal to minus curly P by curly S at constant volume. If we equate equation 1 and 2, then this left hand side of both these equations is same. That means if left hand side of both equations is same, then right hand side equations are also same. That is curly T by curly V at constant S gives you minus curly P by curly S at constant volume. This is our first Maxwell equation. Now, for the second Maxwell equation, we will start from equation of enthalpy change, that is dH is equal to TdS plus VdP. This is our equation 1. Now, if in a process S is constant, that is ds is equal to 0, then we get dH is equal to VdP or dH by dP at constant entropy is equal to volume. Now differentiate this equation with respect to entropy. What we get is curly square h by curly p into curly s is equal to curly v by curly s at constant pressure. This is equation number 2. Now repeating whole procedure in the second stage, if pressure is kept constant, that means dP is 0, then equation 1 can be reduced to dH is equal to TdS or dH by ds. This becomes equal to T. Now once again differentiating this equation with respect to pressure, keeping S as constant. This gives you curly square H upon curly S into curly P is equal to curly T by curly P at constant entropy. This is equation 3, and if we equate equation 2 to equation 3, that is once again left hand sides are equal. This implies right hand sides must be also equal, that is curly V by curly S at constant pressure must be equal to curly T by curly P at constant entropy. This is our second Maxwell equation. So the procedure for both is almost same, just the starting equation is being different. Moving on to the third Maxwell equation, that is curly S by curly P, that is change in entropy with respect to change in pressure at constant temperature, is equal to negative of change in volume with respect to change in temperature at constant pressure. To obtain this equation, we will start from free energy change is equal to minus S dt plus V dP. This is our equation 1. We will follow a similar procedure in which we start with if temperature is constant, then dt becomes 0, or our equation 1 is reduced to dg is equal to V dP or dg by dP at constant temperature is equal to volume. Now differentiating above equation with respect to temperature, what we get is curly square G by curly square P into curly square, not curly square P, into curly P into curly T. This becomes equal to curly V by curly T at constant pressure. This is our equation 2. Similarly, if pressure is constant, that is dP is equal to 0, then what we get from equation 1 is dg is equal to minus of S dt or dg by dt at constant pressure is equal to minus S. Now differentiating with respect to pressure, above equation can be reduced to curly square G into curly T into curly P becomes minus curly S by curly P. Now once again equating equation 3 to equation 4, what we get is curly V by curly T at constant pressure is equal to curly S by curly P at constant temperature. This is our third Maxwell equation. And moving on, Maxwell equation 4 can be obtained by starting from dA is equal to minus S dt minus P dV. This one you can achieve by using the mathematical procedure which we have discussed in the previous 3 equations. Thank you so much.